All right. So let's continue our lesson on electrochemistry and redox reactions and electrochemistry. So last time we said a redox reaction is a reaction that involves a transfer of electrons. And we said that if we can carry out the reduction and the oxidation in separate compartments, then we can get something useful out of it. We can get the electrons to flow through a wire, and we can use it to do electrical work. You know, you can use it to light up a light bulb or move a motor. Okay, so a setup where you have the reduction and oxidation in separate places is called a galvanic cell, also known as a voltaic cell. My pen is not working. Okay, hold up. Okay, problem fixed. So, we said it's a galvanic cell, right? Or a voltaic cell. That's another name for it. Okay. So, as the reaction occurs in your galvanic cell or voltaic cell, electrons are able to travel, okay, through a wire. Okay, so the parts of a voltaic cell would be the anode, okay, half cell. Okay, so you can think, since a redox reaction involves oxidation and reduction, since we're separating them in two compartments, you can say why we have two half cells. Okay, so the anode would be one half cell, the cathode would be the second half cell. Okay, so you have two half cells. Like if you were to set something up like this in the lab, you would put two beakers. Okay, one, you have the reactant and product for the anode in one beaker. So let's call this the anode, and the other beaker would have the cathode. Okay, so normally you'd have a piece of metal sticking out of your anode. That could be part of your reactant reaction. Okay, it could be a reactant or a product, and a piece of metal in your cathode, and then you hook them up with a wire. Okay, and you put a load here, or you can put a voltmeter here to monitor the tendency of the electron to go from one to the other. So a voltmeter would tell you the cell potential, also known as the EMF, or electromotive force. Okay, so that gives you a measure of the tendency of the electrons to flow. That tells you whether the voltage will tell you what the tendency of the electron to flow through the wire is. Okay. Now, to complete this circuit, you need to have something that would allow ions to move between the two compartments. So you have to have what's called a salt bridge. A salt bridge could be something as simple as a damp piece of paper. Like in the lab, we would use a filter paper soaked in an electrolyte solution. Okay, so it has to have ions. So your ions will be able to travel through your salt bridge in order to complete the circuit. Okay, so by definition, oxidation is defined to take place at the anode. So what we call the anode in an electrochemical cell, galvanic cell is also called an electrochemical cell. Okay. Oxidation takes place at the anode, and the compartment or the half cell where the reduction takes place, we call that the cathode. Okay. A good way to remember this, O and A are both vowels. Okay, just to help you prepare for the test. R and C, reduction of the cathode. R and C are both consonants. That's a good way to remember. Okay, so what we call the positive terminal of your galvanic cell is the cathode, and the anode is the negative terminal. Why is that? What do we know happens at the anode? Oxidation, right? What do we know happens in oxidation? You lose electrons during oxidation, right? So in an anode, then you would expect the electrons to come out of your anode. So that's why your anode is considered as your negative terminal. Okay? So in a galvanic cell, the anode is negative, and the cathode would be considered the positive terminal. The electrons would travel through the wire towards the cathode, so the positive terminal is your cathode. So electrons travel from anode to cathode. Now, what about your ions in your salt bridge? How do they move? what happens when negative electrons come out of the anode? What happens to the anode? It becomes positively charged, right? In fact, what happens is typically you get cations. If your metal is a reactant in your anode, cations, metal cations will leave your metal. Your metal will get corroded, and it will positive ions will go into solution. So the solution becomes positive. So to neutralize that, what will happen? Your negative ions from your salt bridge will migrate to your anode. That's why we say the negative ions are anions. Anions in your salt bridge migrate to the anode. Okay? So the anions migrate to the anode, and your cations, the positive ions through the salt bridge, will migrate to your cathode. So again, it is easy to remember. A to A, C to C. Anions go to the anode, cations go to the cathode. And like I said before, historically the word battery refers to two or more galvanic cells put in series, but these days we generally just refer to even one galvanic cell as a battery. Okay? Your common household battery. Now, what would be the standard cell potential for this? If all your reactants and products are at a unit activity equals 1, your reaction quotient is equal to 1. The voltage that you measure is called the standard cell potential, right? So that's the standard reduction potential plus the standard oxidation potential. Or, since the numbers that you look up would all be given as standard reduction potentials, if you don't specify reduction or oxidation, you assume you're dealing with numbers you look up that are reduction potentials. So you say the expected voltage would be, under standard conditions, would be the standard potential in the standard reduction potential in the cathode minus the standard reduction potential for the anode, because you know what happens in the anode is oxidation, so you have to put the reverse of it, so you subtract. Okay, so you might see, depending on what textbook you're looking at, you might see the plus and the minus, just so you get things straight. If they're using subtraction, they're subtracting, then that means they're using standard reduction potentials for both sides. Okay. But if you're adding, then that means the potential for the other standard potential for the other compartment has already been flipped. All right. Let me see if I can show you a nice, and there's a lot of really nice animations on the web that will help you visualize what's going on. And all you have to do is do a Google search for galvanic cells. Here, I've done one for you. Do a search for galvanic cell animation on Google, and this is what you'll find. Okay. One of the better ones, the really good ones, is a flash animation right here. Okay, I'm going to pause the recording here because I can't put this on YouTube because it's copyrighted. I don't want to be infringing. Okay, so let me... All right, so in a typical AA battery, okay, you'll have one terminal marked positive, one terminal marked negative. Where does oxidation take place? Yeah. Huh? Yeah, I did. It's recording now. Galvanic. This is a galvanic cell. So, where would the electrons be coming out of? Got one more clicker missing. Okay. So, at the negative terminal, that's where oxidation takes place. Okay, oxidation takes place at the anode, and that's where the electrons come out. The anode is negative. Okay, so it's negative. Anode is negative. So in a galvanic cell, the anode is negative. All right, here's a good way to remember that the anode is negative in a galvanic cell. Anode. Cathode is positive in a galvanic cell, so cathode. All right. What would be our experimental setup for this reaction? What's our oxidation here? copper becomes copper plus 2, right? So that's a loss of electron. So that means what? That's oxidation, right? So our anode should have what? It should have copper ions, right? And we're going to stick a copper metal in there. Oops, let me put this away right here. So you're going to have you're going to put up a beaker with copper ions. Now you cannot just have copper ions in there, right? It has to be copper something. So maybe copper sulfate, maybe. You can put a solution there. And then you would put a piece of copper metal there. Okay, that's your copper metal. That would be your anode. And then what do you do on the other side? For the cathode, what do you have? You put a solution of silver ions. So maybe like a silver nitrate solution. Okay. So silver with some other ion, negative ion along with it. And then you stick a piece of silver in there. And what do you do next? Hook these two up with a wire, right? And then run it through some kind of a light bulb or a resistor. That way you don't have a short circuit. Okay, you got a light bulb right there. Okay, but to complete this circuit, what would you need? You're gonna need a salt bridge right here. Okay, so you can have like you can use like a piece of filter paper. You moisten it with an electrolyte solution. Or you can put an inverted tube there with a solution with cotton plugs on both ends. Okay, so that would be your setup. Now, how do you determine the cell potential? You can use a voltmeter. I've got one right here. Okay, and so the way a voltmeter is set up is, let me show you some pictures of a voltmeter while you pass this around. Let's do a search for voltmeter images on Google. Here's an example. There's a whole bunch of them. This one looks like the one you have, huh? Yeah. So a voltmeter would have test leads. These are called test leads right here. Okay, so they're usually color-coded. It's red and black, and it's color-coded as to where you plug it in. One of the places where if your leads are detachable, okay, what you would do is you would plug in your black lead to the socket labeled COM, which means common or ground, okay, and then the other lead goes into the other socket. And so what you do is that red lead, the hot lead, you connect that, okay, to one electrode, and the black lead or the ground lead, you connect that to the other electrode. Your cell potential is the absolute value of the voltage reading. Okay. Now, if your voltage reading is positive, that means you are connecting it. That means you're connecting the red to the cathode, okay, and the black to the anode. So the ground lead is connected to the if you connect the ground lead to the anode and the red lead to the cathode, you're going to get a positive reading. But you can try that on a AA battery. If you switch your leads, okay, then you're going to get a negative reading. So don't worry whether you're getting a positive or a negative reading. It just still tells you your battery is alive, okay. All it's saying is that, okay, wherever if you're getting a positive reading, then you're looking at a situation where the black lead is connected to the connected to the anode. Okay. Otherwise, you got it switched. So let's quickly check that to see if you got it. If your red lead of a voltmeter is connected to the negative terminal, so I have a AA battery here. And if I were to hook up the red lead over here, okay, and the black lead to the positive terminal, and my voltmeter is over here. So here's my voltmeter. Okay. Okay. What voltage reading do you expect to get for a new battery? Positive, negative, or zero? What did we just say? Black goes to anode. Okay. It goes to the negative terminal to get a positive reading. So since we did not put the black lead, we did not attach the black lead to the negative terminal, we would get a negative reading out of this. Okay? So that's how you can identify the anode of your galvanic cell. Now, a cell diagram is a shorthand description for a galvanic cell. What you do in a cell diagram is you list all the species that are involved in your cell, starting with, and you have to do it in this order. You start with the inert electrode for the anode, if any. Sometimes your anode half reaction doesn't involve a piece of metal. Then what you do is you have to put something in there, like a platinum wire, to be able to allow the electrons to come out, okay? So usually you would use a platinum wire or a graphite rod, that's carbon, okay? Then you list the anode reactant, just the actual species, the ions or molecules involved, then the anode product. So the anode reactant is the subspecies that is what? Oxidized, and the product would be what it's oxidized to. And then the cathode reactant, and then the cathode product. So the cathode reactant is the species that is reduction of the cathode, and the cathode product is the product of the reduction. And then if you have, again, an inert electrode in your cathode, okay, if your reaction in the cathode doesn't involve a metallic solid, then you have to put something in there, an electrical conductor there, to be able to complete the circuit, okay? And if you want to provide a little more detail, you can specify the physical states or the concentrations of your reactants and products in parentheses, okay, including the inert electron. Now, when you draw your cell diagram, you separate the items that are in the same phase by a comma. So if you have, for example, in your anode, you have iron and with a +2 charge and a +3 charge, you separate them by a comma. If they're in different phases, for example, a piece of silver metal and a silver ion would be separated by a vertical bar, because your silver metal will be a solid and your silver ion will be an aqueous solution. So you separate them with a vertical bar. Okay? If your two compartments are separated by a salt bridge, you draw two vertical bars to separate the anode from the cathode. Okay? Sometimes it's possible to set it up so they're all in one solution. Okay? And in that case, you just do one bar. Okay? And like I said, your inert electrode is usually either platinum or a graphite rod. You have to use that if your reactants are neither one of the reactant or product is a metallic solid for your reaction. Okay? So how would you interpret this cell diagram right here? Which one's the anode? We start with the anode, right? And then you end up with the cathode. First, let's look at the easiest ones to identify right here. What does this represent? That's a salt bridge, right? And so, anode on the left, salt bridge, and then cathode on the right. So what would this setup look like in the laboratory? I would have, okay, two half cells, right? I'm going to have a salt bridge. And what do I have on the right? What's the metal that sticks out of my cathode? Copper. So I'll have a piece of copper there. And I'm going to have copper ions in solution in my cathode. What do I have on the left? Okay, first of all, why is this thing a bar, vertical bar there? Because your copper is a solid and your copper ions is an aqueous solution. So you put a bar to separate them. What about H plus and H2? So you have an acid here with H plus, right? And what do you know about H2? That's a gas, right? So I have to be bubbling in some gas in here. So I have to have some kind of contraption here where I can bubble in some gas. Okay. So maybe a tube that would bubble in some hydrogen gas there, a source of hydrogen, right? And what do I need to have here? Since I don't have a piece of metal in my anode reaction, what do you think is my anode reaction? How is H plus and H2 related? If I want an oxidation half reaction, how can I write an oxidation that involves H plus and H2? H plus H2 will give you what? 2H plus 2 electrons, right? That would be the oxidation. So I would have to stick a platinum wire in here for it to be able to conduct electricity. Okay? So that's what that cell diagram would look like. Okay? All right. Let's talk about delta G and the cell potential. How are they related? If you recall, when we talked about the second and third law of thermodynamics, we identified delta G, the Gibbs free energy, the change in the Gibbs free energy associated with the reaction, as the maximum amount of useful work that you can harness from a spontaneous process. Remember we said, in particular, if you have a reaction that incurs an entropy debt, okay, yeah, and if it's capable of releasing energy, part of the energy has to be released as heat to compensate for any entropy debt, and the rest of it you can harness to do useful work. It doesn't have to be wasted as heat. And this is one way you can harness that energy. You let it run through. You let it drive electrons through a wire. You do electrical work. Okay. So imagine you have a galvanic cell that's discharging. Let's say a mole of reaction occurs. That means n moles of reaction will be transferred from the anode to the cathode. And let's just imagine that throughout that process, the cell potential, the voltage across your galvanic cell doesn't change significantly. Okay, so throughout that process, then you say delta G would be the energy that the electrons will gain when they travel without resistance from the anode to the cathode. And so that's just given by the charge. Okay, so n moles of electrons times the charge per mole. Okay, so negative n moles times negative F will be the total charge transferred. Okay, remember the Faraday constant is a charge per mole, the absolute value of the charge of 1 mole of electrons. Negative F is the actual charge since the electrons are negative. So negative NF right here is the charge of the electrons, transferred, the n moles of electrons transferred. Multiply that by the voltage, that gives you the energy that the electrons will get. Okay? So we did a similar calculation like this earlier, right? In the last lesson. So if electrons are passed through a resistor, then the energy that these electrons gain will just be dissipated as heat. You get your resistor to warm up, okay? Now, if you pass it through a motor or a light bulb, then you're able to convert it into something useful. So a motor, for example, you can use it to lift up an object, okay? You can have it turn a motor. So delta G then we say is equal to negative NF times the cell potential, okay? So that's the significance of the cell potential. It will tell you how much electrical work you can derive from your redox reaction that's happening in your battery, in your galvanic cell. Now, a AAA alkaline battery has a cell potential of 1.5 volts, okay? And a AA, I'm sorry. Same thing with a AAA. So if you measure the voltage across the positive and negative terminal of your battery, it's going to be 1.5 volts. And these are the reactions involved there. So zinc plus 2 hydroxide gives you zinc hydroxide plus 2 electrons. That's oxidation at the anode of your alkaline battery. And then in the cathode, the reaction is manganese dioxide plus water will give you MnOOH, that compound right there, plus 2 hydroxide. Okay, so that's the Those are the two half reactions that occur in your alkaline battery. Now, let's say you're going to use that alkaline battery to lift a 10-gram object. So you let it run a motor, okay? And the motor lifts, turns a pulley, and the pulley lifts an object, a 10-gram object, to a height of a ½ meter. So we have a 10-gram object here. You lift it up to a height of a ½ meter. How much zinc would be used up in the anode? Okay, and if all this happens in 5 seconds, let's say it takes 5 seconds to lift up the object, how much current went through the motor? So here's the series of calculations you're going to do. First of all, you're going to need to figure out how much energy do you need to lift the object. The work that you need to lift an object is equal to force times distance. Remember? Formula for work is force applied over the distance. So force times distance. And what force will you be applying to your object to lift it up? It should be on average, okay, to go from one height to another, okay, the average force you're going to be exerting would be equal to the weight of the object. The force of gravity is mg, right? So mg times the height, and mg is the mass times acceleration due to gravity. That's the weight of your object. So what's our work due to lifting then? What's the mass of our object? 10 grams. So let's put that in kilograms so we have everything in SI. So 10.0 times 10 to the negative 3 kilograms is a gram, right? 10 to the negative 3 kilograms is a gram. Remember, 10 to the third is, kilo is 10 to the third. So 10 to the negative 3 times 10 to the third is 1, okay? Acceleration due to gravity is how much? You remember from physics, physical science? 9.80 meters per second squared. And our height is ½ a meter, 0.500 meters. How much work would that be? An answer for me? 10 times 10 to the negative 3 is 0.01, right? 0.01 times 9.8 times 0.5, 0.049 joules, okay? 0. Kilogram meter squared per second squared is a joule. That is the work that you need to do, okay? And what is this work going to be equal to? That's going to be your delta G, right? So that's equal to moles of electrons transferred, okay? So that's the charge transferred times, okay, let me see, moles of electrons transferred times the Faraday times the cell potential, okay, minus NFE. So we can solve for moles of electrons transferred. What's our N here? N would be equal to 0.0490 joules over, and let's just use absolute values here. So Faraday is 96,500. That's coulombs per mole of electrons, okay? And our cell potential is how much? 1.5 volts. So 1.5 joules per coulomb. 1.5 volt is a joule per coulomb. A volt is a joule per coulomb. It's energy gain per coulomb of charge, okay? So coulombs cancel out, joule cancel out. That gives you the actual moles of electrons that are transferred, okay? So what would that be? 0.049 divided by 96,500 divided by 1.5, and you have 3.39 3.385 times 10 to the negative 7 moles of electron. Okay? Now, that's the actual moles of electrons for the lifting. Okay, that's not the moles of that's not the same N we talked about in our balance equation, because in our balance equation, if you have a mole of electrons, if you have a mole of reaction, that involves a transfer of 2 moles of electrons. So you can see from here, okay, you're transferring 2 moles of electrons for every mole of zinc that's involved in the reaction. So we can now calculate the moles of zinc involved. We can say moles of zinc equals 3.385 times 10 to the negative 7 moles of electrons times 1 mole of zinc is going to be consumed for every 2 moles of electrons transferred. Okay? So that, how many moles of zinc would that be? Divide that by 2. That should be 10 to the negative 7, right? So divide that by 2. That gives you 1.7 times 10 to the negative 7. 2 sig, if we 1.70 times 10 to the negative 7 moles of zinc. Okay? So that's the answer. 1.7 times 10 to the negative 7 moles of zinc. Right? So if all of that happened within 5 seconds, how much current is passed through the wire? What's the definition of current? Current is charge per unit time. Okay? So total charge that's transferred per unit time. So what's the total charge? Our current, this current right here, is NF, the total charge per unit time, right? And our time is how much? 5 seconds. And how much charge did we transfer? 96,500 coulombs per mole of electrons. By how many moles of electrons? 3.385 times 10 to the negative 7 moles of electron. I need some room. Let me redo this. So current is 3.385 times 10 to the negative 7 moles of electrons multiplied by 96,500 coulombs per mole of electron divided by 5 seconds. Okay, moles of electrons cancel out. That gives you coulombs per second. What would that be? So this times 2, that was your moles of electrons, right? Times 96,500 divided by 5. That gives you 0.00653. Okay, so 0.0065 coulombs per second. A coulomb per second is called an ampere. Okay, so that's 1 ampere. So that's a unit of current. So our current here is equal to 0.0065 amps, or 1, 2, 3, that's going to be 6.5 milliamps. Okay, so that's the current that motor is drawing from your battery in order to lift that 10-gram object to a height of 0.5 meter. Okay. What's the relationship between KEQ and the standard cell potential? Well, if delta G is equal to negative NF times the cell potential, then delta G naught, okay, the standard Gibbs energy for a reaction would be equal to negative N times F times the standard cell potential. Now, if you remember from our discussion of the second and third law, we said that delta G is equal to delta G naught plus RT ln Q. That's why your cell potential depends on your Q. Remember we said? Okay, so if you were to make the substitutions here, okay, so delta G is negative NF E cell is equal to delta G naught, which is negative NF E naught cell, plus RT ln of Q, okay, and you divide both sides by a negative NF, that gives you, that NF cancels, that gives you this equation right here, which is called the Nernst equation. The cell potential is equal to the standard cell potential minus, okay, there's a minus there, NF minus RT over NF times natural log of Q. This is called the Nernst equation. This tells you how the cell potential depends on your reaction quotient. What happens to your reaction quotient as the reaction progresses? Eventually, it's going to approach your KEQ, right? All reactions eventually approach KEQ, the reaction quotient. And so, what do we know when it's approached KEQ? Delta G is going to approach 0, right? And your cell potential is going to approach 0. At equilibrium, when your battery is fully discharged, it's not going to put out any voltage, right? So delta G approaches 0, cell potential approaches 0. So we say when the cell potential is 0, that's going to be equal to E naught cell minus RT over NF natural log. And instead of plugging in Q here, we now, actually we do plug in Q here, but the Q is now going to be equal to KEQ. So at equilibrium, we say that 0 is equal to E naught cell minus RT over NF natural log of KEQ. Okay, so if you have a way of measuring the standard cell potential, that will tell you what the equilibrium constant is. So this is one way you can determine the equilibrium constant for a reaction, for a redox reaction. You figure out the standard cell potential. You find a way to measure the standard cell potential. So how would I solve for KEQ if I know my standard cell potential? How would I rearrange this equation? I can say then that E naught cell equals RT over NF natural log of KEQ. And so I can solve for KEQ. It's going to be NF E naught cell over RT. I'm just going to rearrange this. I'm going to move this over there and move this down here. This natural log of KEQ. And then I just take the anti-log of this to get my actual KEQ, right? So KEQ would be E to the negative NF E naught cell, positive NF E naught cell over RT. Okay. Was there a negative? Oh, see, when I move this thing over to the other side, this one, if I move this one over to the other side, it becomes positive. Okay. Or, remember you also said that instead of ln k, you can use base 10 logs. Okay, the alternative form of your Nernst equation, what was it? Here's a math review. Ln of k would be equal to 2.303 base 10 log of k. Okay. So if you take base 10 log, you multiply by 2.303, that gives you natural log. So if you combine that, so this is going to be E naught, this thing right here, instead of that being that, you can say that's the same thing as 0.059 over n times base 10 log of q. All right. In this case, you factor in your 2.303 and then change it to base 10 log. Okay, and we're plugging in 298 Kelvin as our temperature, 0.0592 to be more precise. Okay. All right. So that's how you can calculate. Okay. So let's do some calculations. Let's calculate the reduction, the KEQ for the reduction of iodide by ferric ions. Okay, and then we do the same thing for the reduction of bromide by ferric ions. So if I want to reduce iodide, what should I do? I'm sorry, this should be oxidation. Okay, fix that, please. So I want to oxidize iodide. So what I look up the standard reduction potential of I2. It's that. Okay, and iron is this one. Okay, you have your iron can be reduced to Fe plus 2. Okay, so if it's reduced, it can cause something else to get oxidized. So let's say you want it to oxidize iodine. Okay, so what's the oxidation reaction then? I have to flip this one, right? Flip this to make it an oxidation. I say 2 iodide aqueous yields I2 solid. And I'm just going to leave out the physical states to make things easier to follow. Plus 2 electrons. So what's my cell potential for this one? Oxidation. So oxidation potential is going to be negative 0.53. If you're wondering where I found this, I look it up. Okay. Now, what happens when you do iron? You still have your iron for your reduction. Iron plus 3 plus electron gives you iron plus 2. And the standard reduction potential for that is 0.77. Okay? So what do I need to do to get the overall reaction? To get the balanced overall reaction, what should I do? Electrons lost must equal electrons gained. So what should I have to do with this second step? I have to multiply that by 2. Keep in mind, standard reduction potentials are intensive properties. Even if you multiply your coefficients by 2, the potential remains the same. Okay, so you don't multiply this other side by 2. So if you combine these, you have 2 iodide plus 2 ferric ions, Fe plus 3, yields I2 plus 2 iron plus 2. That's your overall reaction. That's a redox reaction. And what is your standard cell potential here? It's going to be E naught oxidation plus E naught reduction. So negative 0.53 plus 0.77. That would be how much? 0.24. Okay, that's E naught, right? What's my KEQ? E to the n f E naught over RT, right? So that's going to be equal to E, I can say EXP, that's another way of saying E. And what's our N here? How many moles of electrons are transferred in this reaction? N is 2, right? 2 moles. Okay. And Faraday is 96,500. We're going to put everything in SI here, so our standard cell potential is 0.24 volts. Divided by R, we have to use 8.314 joules per mole per Kelvin. And temperature is 298 Kelvin. Okay. And let me just leave out the units to make things easier to follow. So what would that be? 2 times 96,500 times 0.24 divided by 8.314 divided by 298. That gives me 18.70. Okay. So this is E to the 18.70. What would that mean? If I do this, I have to take inverse log, so inverse and then E to the X right here. That gives me 1, 2, 3, 4, 5, 6, 7, 8. 1.3 times 10 to the 8.
Why did you use the positive 0.24?
Why did I use the positive 0.24? It is positive. Yeah, it is positive. Negative 0.53 plus 0.77. Okay, so this is, okay. Oh, this thing right here, F to E, that's fixed notation to exponential notation. That allows you to switch between the two. So this is 1.32, 1.3 times 10 to the 8. Okay, so 1.3 times 10 to the 8. Now, is that a large or a small equilibrium constant? Large KEQ. That means products are favored at equilibrium. This is a reaction that you'd expect to go almost all the way to completion. Okay? So a positive cell potential means it will go far, right? Far towards the product side. In fact, you can relate that to delta G naught. Delta G naught is negative NF E naught cell, right? So the more positive this one is, the more negative the delta G naught is. Remember we said a very negative delta G naught is a reaction that goes far towards the product side. Okay, so the more positive the standard cell potential is, the larger the equilibrium constant. What would be your equilibrium constant if the standard cell potential is 0? E to the 0 is 1. Okay, that would be your equilibrium constant. What if it's negative? E to a negative number would be a number less than 1, so your reaction is not going to go far. So if you have a negative standard cell potential, you're looking at an equilibrium constant that is very small. Okay, so let's try the other case. This time let's do bromide. Instead of 0.53, we're going to use 1.07. So our oxidation potential for bromide this time is going to be so you're going to do 2 bromide yields Br2 liquid plus 2 electrons. The oxidation potential for this is negative 1.07. Okay, so when you add up the two, what do you get? So instead of iodide here, you're going to have 2 bromides. And instead of I2 over here, you're going to have Br2. What do you see here? What's our cell potential this time? You're going to have negative 1.07 plus 0.77. What would that be? Okay, so 1.77 minus, okay, 0.77 minus 1.07, that's negative 0.3. Okay? So that means, this is involved, that means what? This reaction this time is not going to go far forward. It has a negative cell potential, and so delta G here is going to be positive. So what would that be? If I plug in, instead of 0.24, I plug in negative 0.3 over here, what would I get? Let's try that. 2 times 96,500 times 0.3 divided by 8.314 divided by 298. That gives you negative 23.37. Okay. So e to the negative 23.37. Inverse log, make that negative. Okay. Inverse log, that's 7.09 times 10 to the negative 11. That's a very small KEQ. What's one practical application of this in the lab? If you have a mixture of iodide and bromide, and in Chem 110 you'll be doing this experiment, if you have a mixture of iodide and bromide, you add ferric ions to it. Okay, you can separate the iodide from the bromide because the iodide will react. It will give you I2, and then the bromide will not. And then what you can do with the I2 is, what you do in the lab is once you form your I2, okay, so you have your I2 now and your bromide, right? Your bromide stays the same. It doesn't react very well with ferric ions. Your iodide will give you I2. So what you can do is you can add a nonpolar solvent to that, like hexane or carbon tetrachloride. Your nonpolar I2, okay, will be selectively extracted from your mixture. Okay, a nonpolar solvent will preferentially dissolve I2, and so you can remove it and you can have it separated from your bromide. And you can sort of tell from here, okay? Remember, the reverse of this would be negative 0.53, and the reverse of this would be negative 1.07. You say that iodide is has a greater tendency to get oxidized than bromide, right? Iodide is more likely, has a greater tendency to lose electrons than bromide because it's got a less negative oxidation potential, okay? This might be a good time to pause. We're going to talk about electrolytic cells next.